in this video, I would like to take some time to go through chapter 5, which is about earthquakes and taking a look at the layers of the Earth's interior. So everyone is familiar with what an earthquake is, whether you've felt one or not. An earthquake is the shaking of the earth caused by the sudden and rapid movement of one block of rock slipping past another along faults. Faults are fractures in the Earth's crust. Most faults are going to be locked, except for these brief sudden movements that can lead to earthquakes. Earthquakes tend to occur along pre-existing faults where stresses caused by internal forces within the crust have caused those rocks to either rupture or to break into two or more parts. The location where that slippage begins is called the hypocenter or the focus. And the point on the Earth's surface directly above the hypocenter is called the epicenter. So here we can see a fault and the fault trace on the surface of the Earth. And where these rocks slide past one another, creating the earthquake, is called the hypocenter or focus. And here we can see the epicenter there on the surface of the Earth. Earthquakes are going to release this energy in the form of seismic waves. And so we can see these waves being generated here. This is energy that's going to travel through the lithosphere and through the Earth's interior. An earthquake, as you can see on this image, is going to generate waves that radiate outward from all directions. So where we have the focus of the earthquake, we can see these waves are going to spread in all directions. Thousands of earthquakes occur around the world every day. Most of them are too small to be felt by anyone. A lot of them occur in deep ocean floor, so people aren't anywhere around those, so not going to, feel those either. So how did we figure out what caused earthquakes? Well, we know from looking at fossil records that there's been uplifting, right? That a lot of the Earth's crust, or large sections of the Earth's crust, have been uplifted or thrust upward because we have found marine organisms on the surface of the Earth, or fossils of marine organisms on the surface of the Earth. We also can look at different areas and see evidence of subsidence. So that describes vertical displacement. We also can see that fences and creek beds have been offset. So we know that there's also lateral movement that occurs. But the actual mechanism that caused or led to the generation of earthquakes was not really explained until after the Great San Francisco earthquake of 1906. And we had a geologist named H.F. Reed who conducted a study after that earthquake. This earthquake was accompanied by horizontal surface displacements along the northern portion of the San Andreas Fault. The Pacific Plate moved forward almost 10 meters past the North American Plate in this earthquake. What Reed concluded from his investigations is that differential stress is going to lead to the bending of crustal rocks. And this figure kind of shows what's happening here. So you can think of this as like a person who is holding a stick in their hands. And as they start to bend the stick, put pressure on the stick, frictional resistance is going to keep the fault at first from rupturing and slipping. But at some point, the stress that's applied is going to overcome this friction, and the slip or slippage is going to occur. So if you think about bending a stick, as you bend it, you're putting force, but the force that you're applying isn't enough to overcome the strength, essentially, of the wood, of the stick. But eventually, as you continue bending, you're going to get breaking. Once that occurs, once that slippage occurs, it allows the deformed or the bent rock to snap back into its original stress-free place, and that is what leads to the waves that originate out from that point. Reed called this springing back behavior elastic rebound, because the rock kind of behaves elastically, kind of like a rubber band would. Now, earthquakes can be preceded by what we call foreshocks and followed by aftershocks. So the foreshocks are earthquakes of a smaller magnitude that can precede the major earthquake. These are not always present. Sometimes they may occur years or even months before the earthquake. Sometimes they may occur a couple of days or hours before a major earthquake. So there's no really good way to predict an earthquake once foreshocks happen. Aftershocks occur because the crust is still trying to kind of get used to that displacement that has occurred. And so as those rocks kind of continue to move, they can generate more earthquakes. Aftershocks are typically smaller. They do not generate as much energy. They diminish in frequency as time goes by. If we look at the slippage that occurs along faults, we can use our plate tectonics theory that we've already discussed to explain how these large earthquakes are able to occur. Faults associated with convergent and transform plate boundaries are the source of most of our large earthquakes. Most of our strongest earthquakes occur along convergent boundaries. Remember that with convergent boundaries, this is where one plate is colliding with another, and this results in compressional forces. And these forces cause thrust faults across the Earth's surface. When convergence causes the subduction of oceanic lithosphere under another plate, like we see here, the area of contact between them causes a megathrust fault. It can be several thousand kilometers long, and they can remain locked for decades or even centuries. But as this subducting plate, slowly descends underneath the overriding plate, it drags and can bend this leading edge. So where we see the overriding plate, this leading edge can get bent here. And as it's being bent, as the subducting plate continues, eventually those frictional forces are going to be exceeded, and the overriding plate is going to snap back into place. And that generates an earthquake. And the magnitude of that earthquake is really dependent upon the size of this zone of slippage. Now, seismology is the study of earthquake waves. And it dates back almost 2,000 years ago to when there were attempts in China to determine from which direction the waves originated. So we use a seismograph or a seismometer to measure earthquakes. What we have is this seismograph that has a weight suspended on it by a wire. And it's attached to this support column with a pivot. So as forces are applied, this weight starts to move. And since it's hung there by a wire and it's got a pivoting on here, it's going to pivot more when there's more energy applied and pivot less when there's less energy applied. So most seismographs are designed to amplify the motion of the ground so that very weak earthquakes can be detected. And even an earthquake that happened in another part of the world. There are several different types of seismic waves that occur. First, we have body waves, which travel through the Earth's interior. And with body waves, there are two types, primary or P waves and secondary or S waves. P waves are push-pull waves. They are due to compressional motion. They are going to compress and stretch rocks in the direction that the wave is traveling. And they can travel through solids, liquids, and gases, so all forms of matter. And they have the greatest velocity. So they're the fastest of all of the earthquake waves. F waves. Or secondary waves, they shake the particles at right angles toward their direction of travel. And they can only travel through solids. Their velocity is slower than P waves. So P waves can change the volume of intervening material by squeezing it or compressing it and stretching it, but S waves change the shape of the material that transmit them. But again, secondary waves can only go through solids. Surface waves have a complex motion. One type causes the Earth's surface to move up and down, kind of like the waves on an ocean moving the ships. And the second type of surface waves causes the Earth's surface to move from side to side. So we've got two different types, but these move the slowest of all of the waves. So how do we locate where an earthquake has occurred? So how do we locate the epicenter? We can use seismograms from at least 3 different seismic stations, and we use what's called a time travel graph to determine the distance that these waves have traveled. And then we use a compass to draw a circle with the radius from each of the seismic station, and where the circles intersect is going to be our epicenter. So in this example, we have 3 different seismograms, one from New York, one from Nome, Alaska, and one from Mexico City, Mexico. And we look at these 3 and we look at the time it takes from the first P wave and the first S wave to occur on the seismogram. And then we look at this time travel graph where we can see our S wave curve, we see a P wave curve, and we find the time interval between them, track that down, and that's going to give us our distance from the epicenter. And then we use triangulation. So here are our 3 stations, Nome, New York, and Mexico City. And then we use a compass like this to draw a circle from each one, and the spot where they meet right in the middle is going to be the epicenter. And of course, we know that the epicenter is the surface location of where the earthquake occurred. And we don't always know depth. We don't always know where the hypocenter or the focus is. So how do we determine the size of an earthquake? So we can measure an earthquake by intensity and magnitude. Intensity is observed by looking at the amount of damage. So we look at property damage. And we have a scale called the Modified Mercalli Intensity Scale that we use for intensity. And here is this scale, and you can see that we're looking at damage. And, you know, if we go down into, you know, get into the 6s and 7s, you know, damage slight, damage negligible in buildings of good design. And then we start getting into 9 and 10, damage considerable. Most masonry and frame structures are destroyed. And then 12, damage total. Objects thrown up into the air, waves actually seen on the ground surfaces. Magnitude is the amount of energy that is released at the earthquake source. And we often use the Richter scale for this. And so if you hear news coverage of an earthquake, what they're stating there is the Richter scale. And this is based on the amplitude of the largest wave. The Richter scale was developed in 1935 by Charles Richter, who worked at Caltech. And he was the first to use this type of scale. And when we look at the Richter scale, a 10-fold increase in wave amplitude results in an increase of 1 on the scale. And then that is multiplied by about 32 times in the difference of energy release. So it's a logarithmic scale. So a earthquake that is magnitude 4 is 10,000 times the amplitude of one that is a Richter scale of 1. So it's a logarithmic scale. So you have to think, you know, if we talk about an earthquake that's, you know, a 7 or an 8, we're talking about an earthquake that is much more destructive than a 5 or a 6. We also have what's called moment magnitude, and for this we can measure medium and large earthquakes. This estimates the total energy that's released during the earthquake. So not specifically by the largest of the waves, it's the total energy that's released. And this is looking at the amount of slip that occurs on the fault, the area of the fault that ruptured, and then what is the strength of the rock where the earthquake is occurring. So this is a moment magnitude, and here you can see, you know, 9s. We're talking about very few of these. This is we had a 9.5 in Chile in 1960. The Alaska earthquake in 1964 was a 9.2. We had an earthquake in Arkansas in 2011 that was between a 4 and a 5. And then we have, you know, hundreds of very minor and minor earthquakes really every day. So what causes earthquake destruction, or what, you know, makes one earthquake that's a magnitude 4 a lot worse than another earthquake that's a magnitude 4? So we have to look at what are some of the forces that these vibrations can trigger. So we look at the intensity. Okay, so we have to look at how much energy is generated. And then how long does it last? Are we talking about an earthquake that's, 10 or 15 seconds, or are we talking about an earthquake that goes on for 2 or 3 minutes? What is the material where the structures are located? Is it silt? Is it sandy, clay, bedrock? So what type of material are we talking about? And then how is the structure designed? Is it designed to be able to withstand earthquakes or not? So we know destruction results from ground shaking. That can lead to wave amplification based on whatever that ground material is. So some types of ground material are going to amplify the waves, make them worse than other types of ground material. And then we have something called liquefaction. Liquefaction is when you have a situation where some type of saturated material becomes fluid, almost liquid, and things that are underground may float up to the surface. So basically what happens is as the earth is shaking due to the earthquake, it can cause stream deposits or sandy areas to be transformed into liquid. It disrupts those water molecules that are in there, and this liquefaction can mean that an area where buildings once were that seemed stable is no longer capable of supporting those buildings. Underground storage tanks or sewage tanks can float to the surface. In 1989, the big earthquake that was in California, what we call the Loma Prieta earthquake, foundations failed and sand and water literally shot up from the ground like geysers due to liquefaction. And so here is an example. This is from an earthquake in 1964 in Japan. So these buildings were built on sediment that seemed strong enough to hold the buildings. They had been there for many years, but it was unconsolidated sediment. It was more sandy. And as those water molecules started moving due to the shaking from the earthquake, the building started to sink and fall over. We can also have destruction from earthquakes that causes fires. We have the rupture of gas lines that can lead to, flammable material, and therefore we have fires. We can have landslides and ground subsidence or the ground slipping. And then, of course, we can have tsunamis. Tsunamis occur when the ocean floor becomes displaced and all of that water has to go somewhere. Tsunami is actually a Japanese word that means harbor wave. And most of the time when we get tsunamis, these are caused by earthquakes that occur on the ocean floor, but not always. But usually we have a megathrust fault that is going to lift up a slab of seafloor, and this starts out with a series of waves, and as it passes through water, the wave becomes bigger and bigger and bigger, and tsunamis can advance through the ocean at considerable speeds, like 500 miles an hour. So a tsunami out in the open ocean can pass undetected because it's not unusual to have, waves that get fairly high out in the open ocean, and there's nobody out there monitoring them. But once the waves enter into the shallow areas close to the coastline, they start to slow down, and the water kind of starts to build up, and that's what makes the waves so high. In your book on page 142, there's a link to an animation of the tsunami that was generated off the coast of Sumatra in 2004. This was a particularly devastating tsunami, killed hundreds of people. It happened around Christmas Day. I think it was on Christmas Day, and our time, I think it was December 26th there. But there was an earthquake of 9.1 that occurred on the ocean floor, and the as the tsunami came, there were no warnings at the time, and this tsunami swept across the island of Sumatra and killed, thousands of people. In 2011, there was an earthquake in Japan, and this led to a tsunami that caused damage at the Fukushima nuclear complex, and this caused a meltdown of the nuclear reactors, and there was radiation release. So in addition to the effects from this earthquake that occurred, now you had devastation that occurred because of the nuclear meltdown from the nuclear power plant there. So where do most earthquakes occur? So we've said that they mostly occur along converging and transform faults. So 95% of all of the energy that's generated from earthquakes occur in just a few narrow zones across the Earth's surface. We have the Circum-Pacific Belt and the Alpine Himalayan Belt. So the Circum-Pacific Belt, as you can see, kind of goes around the Pacific Plate and its boundaries with other plates. And sometimes we call this the Ring of Fire, because not only do we see a lot of earthquakes occurring here, we also see a lot of volcanoes. The other place where we see a lot of our earthquakes is in the Alpine Himalayan Belt. And so the Himalayas are right here. This is from the Indian Plate kind of coming up into the Eurasian Plate. So we have a lot of earthquakes that occur in this area as well. And then you can see along our ocean ridges, like the Mid-Atlantic Ridge, the East Pacific Rise, the Southwest Indian Ridge here, we can also have a lot of earthquakes that occur there as well. Now, east of the Rockies, there's a picture in your book on the bottom of page 145 that looks at earthquakes that occur east of the Rockies. So when you think about earthquakes, especially in the United States, you think about California probably, or Alaska. And of course, that is where the majority of the earthquakes in the United States happen. However, there have been other earthquakes in the central and eastern United States that have caused significant damage. And we have one that's located not that far from us. So in northeast Arkansas, we have the New Madrid Fault. It runs in around New Madrid, Missouri, down into Arkansas. And in 1811 and 1812, there was a series of 3 earthquakes that occurred there, December, January, and February. And if it had occurred in today's times, instead of 200 years ago, you would have thousands of people that would be injured or killed, and damages would be in the billions and billions of dollars. With the earthquakes in 1811 and 1812, there were a lot of eyewitness reports of some of the damage that occurred. We do know from reports that the earthquake generated enough energy to ring church bells all the way in Pennsylvania. It caused a section of the Mississippi River to flow backwards for a time, and it led to the creation of several lakes in the Missouri, Kentucky, Tennessee area close to the Mississippi River. So it was a devastating series of events that occurred, and we have not had a major earthquake on the New Madrid Fault since 1811 and 1812, that winter. The greatest historical earthquake that occurred, though, in east of the Rockies was in Charleston, South Carolina in 1886. 60 people died. Within 8 minutes, they felt the effects from this in Chicago and St. Louis. In Charleston, more than 100 buildings were destroyed, and the ones that were left, about 90% of them sustained significant damage. So the last section of the chapter looks at predicting earthquakes and forecasting and earthquake warnings. So we don't really have a way to predict earthquakes. There's been no reliable method that we have found to predict earthquakes. We can look for precursors. We look at foreshocks. We can look at elevation changes in the ground. We can look for areas of slippage in the faults. But we don't really have a way to predict them. Looking long range, we have what's called paleoseismology, which is the study of past earthquakes. We have this idea of what we call a seismic gap. And these are areas where there hasn't been an earthquake in a really long time, like at the New Madrid Fault. That earthquakes are repetitive. They happen along these faults, and eventually another one is going to happen. So what is the gap? In some areas, we can really use past data to predict the frequency along earthquakes or along faults, and that can allow us to say, hey, we were getting earthquakes every, 135 years. It's been 140 years since the last one, so, we're due to have an earthquake at some point soon. So how can we minimize hazards? Well, we make sure our buildings are as earthquake resistant as possible. We can do the best we can with that. I mean, we know that there are ways to structure buildings and have, building codes that make them less likely to fall, but we can't cover every earthquake magnitude, for that. We can retrofit dams and bridges to be stronger and able to withstand forces. A lot of times this cross bracing allows buildings to be honestly a little bit flexible, to allow them to be able to shake a little bit without instantly falling. But obviously there's a cost factor that comes with that, and we're not able to retrofit every building. Earthquake warning systems. P waves are less destructive and they travel faster than the S waves and surface waves. They can kind of be used to provide a little bit of a warning system. So in Japan, they have a system that causes power generating facilities and bullet trains to shut down once those P waves are measured. During the 2011 earthquake that I was talking about a little bit before, they sent an automated alert to the television stations and more than 50 million telephones throughout Japan, and that gave them about a 10-second opportunity to take cover. Further south, in Tokyo, they had about an 80-second warning before the strong shaking got there. So 10 seconds doesn't seem like a lot, but that would be enough to get you, to safety, get you out from underneath power lines, to be able to take cover, to seek shelter, cover your head. And then, of course, again, 80 seconds, a minute and a half, not that long of a time, but it could allow you to get to a safer location. We don't have any of that in the United States at this point. So, studying earthquakes, specifically P waves and S waves, has allowed us to learn a lot about the interior of the earth. We know that P waves can go through solids, liquids, and gases, and S waves can only go through solids. And looking at the travel times of those waves has given us kind of an idea of what is in the Earth's core. So when we look at earthquake waves, they can go, they can be refracted. So they don't take a straight path through. They follow these curved paths because the seismic velocity is going to increase with depth. So as we go deeper into the Earth's core, we get increasing pressure, and that causes those waves to be refracted and not travel in a straight path. So the layers of the earth are based on their physical properties. So we have the crust, which is the thin, rocky outer layer, and this is where, we have the continental crust and the oceanic crust, like we talked about with plate tectonics. It varies in thickness. Oceanic regions are the thinnest, followed by our continental crust, and then in the mountainous regions. With the continental crust, the upper crust is granitic and the lower crust is more basaltic. Oceanic crust is primarily basaltic, and we know that the oceanic crust is younger because of the drilling that was done throughout that study back in the 60s, 70s, and 80s, that the oceanic crust is younger than the continental crust. Then we have the mantle. The mantle occurs below the crust to a depth of about 1,800 miles. The uppermost mantle, what we call the asthenosphere, is igneous rock peridotite. And then when we look at the core, the outer core, the S waves can't pass through this because it's liquid. It is composed of an iron nickel alloy. And then the inner core behaves like a solid, even though it's liquid, behaves like a solid because there's so much pressure being exerted by all of the other layers. So here we can see we've got the crust, our mantle, the upper mantle being the asthenosphere, and then the lower mantle. Then we get into the outer core, which is liquid, and finally the inner core, which again, because of the pressure, is going to be solid. So that takes us through a look at the Earth's surface. And then now that we've covered our Earth's surface and looked at earthquakes, we'll move on to volcanoes.